Hello again. This is notes for section 9.3, applications of differential equations. And those applications that we're interested in particular, are the applications of exponential growth and decay. Only difference between those two is just having a positive or negative percent increase, decrease, and logistic growth. There's kind of logistic decay too, but we're not going to talk about that. All right, let's talk about exponential growth and decay first. You have actually studied this, I think in some detail in pre-calculus. And you may have even seen it as early as Algebra 2. So now we just have the tools of calculus to help us understand what's going on. So I'm just going to jump right into some examples here. Let's start with this. Let's say we're given this situation. A population grows at, let's scratch that at. Population grows proportionally to the actual population. If the constant k of proportionality is k is equal to 0.02, then there's a few things that we can do here. Let's first write the differential equation for this situation. So let's see. The rate a population is growing, that's the rate it's growing at, that would be, I'll say dp dt is equal to, it's directly proportional to, that would be k, and we know the k is 0.02, to the population. So that's the differential equation. And this is what differential equations for exponential growth and exponential decay look like. The growth rate is directly proportional to, be some constant there, the amount of stuff that we have. In this case, it's population. So notice that, like in our old, more traditional derivatives, if you want, we'd have dy dx equals, and then be some x's over here. In other words, the function over here had this variable in it, the dt, but this one has the top variable. So it's like a dy dx equals some function of y, right? So there's our differential equation. So part B, we might say something like this. Solve this differential equation for the initial condition if the initial population is equal to, let's say, 1,000. Well, how do we solve this differential equation? We separate the variables. That would be 1 over p dp is equal to 0.02 dt. Right? Just like we've been doing. Separate the variables, all the p's on this side, all the t's on this side. And then we integrate both sides. It gives me natural log of p. You might think, where are the absolute value signs? Well, the population can't be negative, so I don't actually need them. But if you put them there, that's okay. is equal to 0.02t plus c. Right? And then we've seen lots of examples of this type, so we're going to exponentiate both sides. So e to the natural log whatever, that cancels out, gives me p is equal to, this constant can move out to the front, c e to the 0.02 t. And we know that the initial population at time 0 is 1,000. So plugging those values in, that would give me, trying to solve for c here, right? 1,000 is equal to c e to the 0.02 times 0. So e to the 0 is just 1. So c is equal to 1,000. That gives me the population at any time t is equal to 1,000 e to the 0.02 t. Now look, we got that result using calculus, but I'd just like to point out that if you remember the Pert formula and you recognize that this is exponential growth, you can make short work of this problem. If you say, hey, wait a second, this is a Pert problem, in other words, p e to the rt, where this is the initial amount and this is the rate that it's growing at. And you can see that the initial amount, 1,000, and there's our constant of proportionality, that was our rate, 0.02. So you can make short work of that, but you can see the calculus is not hard to get you there. Okay? Now we could be asked other questions about this. So we could say, let me just make a little more room for myself here. I'll say part C of the same problem. We could say, so given the model from part B, which is population is equal to 1,000 e to the 0.02 t, how long does it take for the population to double? Fair question, right? You've done things like this. You did this in pre-calc. All right, well, let's see. Our population is starting at 1,000, so double that would be a population of 2,000. So we're talking about when the population is 2,000 from its initial 1,000, then what is the t? So we're trying to solve for that t there. And you divide both sides by 1,000. You might notice at this step here, it didn't actually matter what the population doubled from. It could have gone from 1 million to 2 million, it could have gone from 1 to 2, and when we divide this, you're just going to get a 2 over here, right? Doesn't matter what it doubled from. Think about that for a minute. If that gives you pause. Now take the natural log of both sides of this. Natural log of 2 is equal to natural log of e to the 0.02 t. Well, the natural log of e to the something, that cancels out. These are inverse operations, or inverse functions. So t is equal to natural log of 2 divided by 0.02. And you can put that in your calculator and see what that is. My calculator, oh no, there it is. Thought it was out of reach. It's right here. So let's just go ahead and do that. Natural log of 2 divided by 0.02. So it takes about 34.7 years, assuming that our time is in years. You might say, hey, that's a long time. Well, I mean, populations don't just go around doubling every day now, do they? It should take a long time. And this 0.02 is like a 2% population growth. Okay, let me do one more example for you. do some money. Do a quick example and teach you something about APR, what that means. So let's say we have money in an account invested at, let's say, 3%. Let's say 2.3%. I think I did 3% in another problem somewhere. So 2.3% compounded continuously. All right, so what does the differential equation for that look like? The differential equation is going to look like the, let's see, the amount of money. I'm going to use P again, for this time it will be like principal instead of population, is equal to 0.023 times the amount of money in the account. Right? The general solution, I'll leave it to you to do the calculus if you want, but recognizing that this is exponential growth, you can just apply the Pert formula. That means principal at any given time is equal to the initial amount, that's like our C right here, times e to the RT. Right? This is like our C. And remember, in the last problem, the C just turned out to be however much stuff you have at time 0, right? Because e to the 0 just gave us a 1 there. All right, so part C, given that the initial amount is equal to, let's see, how much money should we put in there? How about $10,000? Find the amount of money after, how about 5 years? So that would be, P of 5 would be equal to, if the initial amount is 10,000, I get 10,000 times e to the 0.023 times 5. And let's quickly pop that out of the calculator. So I've got 10,000 times e to the 0.023 times 5. That gives me $1,218.73. We'll let the bank keep the fraction of a penny there. $1,218.73. Right? That's what you get for waiting patiently for 5 years. And now, last I want to teach you a little bit of something. If sometimes you see at a bank, actually almost all the time you see it at the bank, if they're advertising a like a CD, which is like a way of depositing money that you're not allowed to touch for some fixed amount of time, that allows you to get a higher interest rate than just like a regular savings account, which has a very, very small interest rate. So let's say they're advertising a CD at 2.3%. Well, next to that number, they're going to have an APR, which is like your annual percentage rate, I think is what that stands for. And what that other number is, it'll be a little bit higher than this. They're just figuring out how much you're actually going to get after a year. So if we started with, and remember that the amount you start with actually doesn't matter. So we could start with 10,000 or we could start with $1. Doesn't really make any difference. The percent that we're going to find here will end up being the same. So we'll just go ahead and do it with the 10,000. We want to figure out how much money do I have after a year if I invest an initial amount of $10,000. 1 year. So let's see. After 1 year, that's exactly the calculation I have in here. So let's do second entry, except we're going to do 1 year instead of 5. We have $10,232. $232 and 67 cents. All right. Now, what's the actual percent increase from 10,000 that I started with to this? Well, with 10,000, it's pretty easy to see what that number is, and you can see it's close to this. But my APR is the actual percent increase here. It's actually 2.3, and the bank might round it to 3 here. They might say, look, like the advertised rate is 2.3%, but your actual APR is 2.33%, right? Because the interest is being compounded continuously, you're actually making a little bit more than 2.3% per year because you're making interest on top of your interest. So they will advertise that rate to make it look a little bit more attractive, even though the actual rate that's being compounded continuously is 2.3%. You'll see a question like that later in the sheet that I give you. Okay, now, logistic growth is another type of growth that's described best by differential equations. And the model for this is, and I'll do it again with population. We might have a population that is increasing at some rate, k. Now if I just wrote this, that's exponential growth, right? But there's another factor here in logistic growth. It's like a limiting factor. The limiting factor looks like this. I think our book uses a capital A for this constant here, so I'll do that. I've seen it as different things in different books, but so there's something happening here. When P is much smaller than this number A, then 1 minus this very small fraction is just very close to 1, so it just behaves very close to the exponential growth model. But as P becomes closer and closer to A, in other words, as this comes closer and closer to 1, this 1 minus this number gets closer to 0, and it drives the derivative down to 0. So it starts out like exponential growth when P is very small, and then it flattens out as this gets closer and closer to 1, and therefore this gets closer and closer to 0. So it doesn't matter how big your percentage or your population is, if this becomes very close to 0, it's going to drive the slope down to 0. What this looks like, this is very important to understand, is something like this. If we start with an initial population of whatever, it starts out looking like exponential growth, and then as the P gets closer to A, this is at A, it gets asymptotically close to here, to that population. And we call A, this is the carrying capacity. The carrying capacity of what? Well, it's like the carrying capacity of the whatever environment or situation is supporting that population because of limited resources and whatever other factors. This turns out to be a better model for lots of different population growth situations. I think we talked about that a little bit in class the other day. Now here, there's an inflection point. And this inflection point always happens at 1/2 of the carrying capacity. That's where the rate of growth goes from increasing to decreasing. Of course, that means inflection point means the second derivative would be 0, right? And we'll do a little example with that just in a second here. Okay? So really, it's possible to do separation of variables and solve this equation, but it is a big, giant mess. And it's not anything that you're ever going to have to do. If you're interested in seeing what it looks like, what the solution looks like, I can refer you to, our book does not do a very good job, but there's another book that I have that does a pretty nice job. Maybe I'll make a video of that that will be optional. We'll see if there's interest in that or not. but I can refer you to another book too if you're interested in seeing that. We're really just more interested in working with it in its differential form, which is much nicer, believe me, than the actual equation for that curve. But just so you know, it is separable. You can get all the p's on this side, and you can do some fancy calculus. It involves partial fractions. It's a super fun exercise. So you can check that out if you're interested. Just let me know. All right, so quick example. Let's say we have a population that is modeled with a logistic growth model, and it's modeled by this equation. dp dt is equal to 0.02 p times 1 minus p over 5,000. So let's just analyze this differential equation and see what we can figure out. First of all, say in part A, if p is small, then dp dt is approximately equal to, if p was very small, like much less than 5,000, then, well, this would be 1 minus some very small fraction. So it's about 1, right? 1 minus something very small. So it would just be pretty much like 0.02p, right? In other words, when p is very small, at the beginning of this population growth, it behaves very much like exponential growth, right? This is the differential equation for the Pert formula for exponential growth with a rate of 0.02. So that's important to note that. Second, what's the carrying capacity? In this case, the carrying capacity is, well, what would make this equal to 0? 1 minus, this would have to be also equal to 1, 5,000. There's one AP question that you're going to see, I think, in your practice multiple choice, where this number is not 1. So you just have to make sure, the important thing is this entire thing has to be equal to 0. So if this is not 1, you just have to do a little bit of algebra. So here the carrying capacity is 5,000. What else can we ask about that? Let's see, where's the inflection point? Inflection point? Well, you could say, well, it's when the population is 2,500, but let's actually show that that's true. Let's actually take the second derivative of this. Now, before we do that, it's going to be a little easier if we distribute this. That's 0.02p, distributing that here, minus 0.02 over 5,000, I'm just going to leave it like that, p squared. Okay, now when we take the second derivative, that gives me dp second derivative of that is equal to the derivative of this. And remember that p, this is like the y variable, so every time I take the derivative of one of these, dp dt is going to pop out. So that's the derivative of that is 0.02 dp dt minus, and then the 2 comes out here, 0.04 dp, oops, sorry, 0.04 over 5,000 p, right? That's the 2 coming out here, just in the power rule there, but I just took the derivative of what's like the y variable, so it's dp dt, right? And are we off screen there? So the second derivative, sorry, I think I mixed my 2's up there, that should be like that. And then we could do a little factoring here. I could factor out the dp dt times 0.02 minus 0.04 over 5,000 p. So you can plug the whole thing back in there, and we know when this is equal to 0, right? But that's not the solution we're looking for. We're looking for when this is equal to 0. You can think about what's the meaning of this being equal to 0. Well, when it's actually at the carrying capacity, sometimes that carrying capacity is called the stable equilibrium of this. In other words, if the population started out at 5,000, then the derivative would be 0. In other words, you'd just get a horizontal line there. So of course, in that particular case, the second derivative of a horizontal line or any other straight line is 0. But that's not the interesting inflection point that we're interested in here. We're interested when this part's 0. So solving that, I'll leave the algebra to you. You should get p is equal to 2,500. So just in case, I mean, you should know the inflection point happens at half the carrying capacity, but it's pretty easy to show that just finding the second derivative, right? The work would look like this, just in case you're asked to show the work that leads to that answer. And then the very last thing I'll ask is, sometimes I like to throw a limit question in here. What's the limit as as time approaches infinity of p of t? As time goes on and on and on, what's the limit of the population? Well, it's just the carrying capacity, right? It's just going to get closer and closer. And, sorry, I said that was the last thing, but this really will be the last thing. What does the slope field look like for a logistic curve? It looks like this. At the carrying capacity, we get horizontal lines like this, and we get lines getting closer to that, right? And then steeper, and when are they steepest? They're steepest at the inflection point, right? Half the carrying capacity, and then they go back to a little less steep, and a little less steep again, and then the 0 is called the unstable equilibrium. And you might wonder, well, what if you started up here? Well, if you plug values in, you'll actually find that the slopes above the carrying capacity will direct you back down toward it. So for example, if you started with an initial population here, your population curve would look like this. If you started here, your population curve would look like this. And the lines underneath it, actually, they don't really have much of a meaning for us because they'd be negative population, but if you plug in the numbers, they plunge downward like this. But what does that mean? That's negative population. So slope fields for logistic curves look something like this, and you're going to see one of those, I think, in a free response practice. So it's worth knowing that this is what they look like. You've got this horizontal asymptote showing up. Shouldn't be any surprise here at 0 and at the carrying capacity, and also that if you start above the carrying capacity, it goes back down toward it, which should make sense. If you think about like a population of deer, for example, that is too big for the resources that are available, well, that population will start to die off until it gets closer to that population that can be supported, right? Population will decrease until it gets toward that equilibrium. All right, here's applications of differential equations.